we've basically said that we can, I guess recap is recapitulation, capitulation. And so we have talked a little bit about our first form of PDEs. And our first PDE that we're dealing with is the so-called groundwater equation. And it looks something like this. Hydraulic conductivity, specific storage. Let me write it the way we've done it. We've written it in head, of course, haven't we? So let's go back. So I'm just going to swap out that P with H. So we've written in terms of hydraulic head. We've written it in terms of specific storage and the rate of change of head with respect to time. And the hydraulic conductivity, this would be what it would look like as 1D. We've said that we can take that, and we spend a large part of last time we met taking this and rewriting it as a algebraic equation, which had the same dependent variable locked into it. And we looked at what these individual matrices might look like. So these would be magnitudes of nodal heads that we have that describe the system. These are rates of changes of those heads defined only as at nodes. And we saw that for this matrix, the K matrix was defined as being something that looked like an integral, a term which related to the kinds of elements we had, a term which related to the constitutive equation which was of interest to us, in this case it's Darcy's law, and an integration. And we had originally, if we ignore this transient term here, in other words, if dH dt is equal to 0, it's not changing in time, so the pressure or the head profile across our system, if you look at it now, it looks the same in 2 days and 10 days, it doesn't change at all, then this, by definition, is the mathematical representation of that, in which case this term disappears, and we just end up with an expression that is kh equals q. And we looked at how to define that and solve it in 2 ways. The first time we met, I think, or the second time we met, we solved it just by writing Darcy's law, in which case we could get the essence of this K matrix. Last time we derived it in a slightly different way in terms of some subcomponents. And if you remember very straightforwardly, those subcomponents are written below, but the constitutive matrix D is something that links fluxes to gradients of head, gradients in space, if you like, if these are matrix equations, which we could also write as, in our shorthand from last time, it was K multiplied by, we use H comma, is the mechanics symbol for differentiation. And so we know exactly what this is. We know that the A matrix allows us to link nodal values of heads with, in one dimension, the gradients of those heads in space, which is really just dH dx, if it's one-dimensional. And so that's what this term is. And A transpose is just the matrix transpose of that. And I think the only other thing that we did was we took this integral of whatever over a volume, and we changed it into an area times an integral over length, just from this fact that if we looked at this element, it has a cross-sectional area, so that's y and z, and x is in the direction, the length of the element, if you like, and so the cross-sectional area of the element that we're dealing with could be represented by by just this. And we rationalize this based on, you'll remember this picture here. For our little beam element, it looked exactly like this. And this area, which is constant along the length of it, is just A. And so that was our way of defining the expressions. So we did it just heuristically, if you like, by writing Darcy's law, and we did it using the Galerkin method, which ultimately gave us this expression here. But we showed that each of the expressions are the same. We did look at this discussion last time, or maybe a week ago today, to talk about the fact that this expression that we have here is exactly the expression that we have that represents a second-order PDE. And of course it follows exactly because this is a second-order PDE that we're representing. And so whether we're looking at displacement gradients for stress-strain problems, or concentration gradients for Fickian diffusion problems, or pressure gradients or head gradients that drive flow in groundwater flow equations, this expression will be exactly the same. And all that will change is that the individual components that relate to this. So if we write it in terms of a solid mechanics problem, then this is that strains are related to displacements at the nodes multiplied by this transform matrix here, which means that it takes displacements and makes them into displacement gradients, du dx. That stresses are related to strains through Hooke's law. This, instead of being hydraulic conductivity, is Young's modulus. And that displacements at a point are mapped from displacements defined at the nodal points through this shape function term. Remember, this shape function term was the tent that was mapping all the displacements from individual nodes onto one particular point, and it's what we also call this weighting function, if you remember from last time, that we applied in applying the Galerkin method. So far we've done everything to be able to define basically what the expression should be for solving a second order PDE, which is of course what we're dealing with. We made the point last time that if we were solving the other parts of this equation, we'd want to know what a zeroth order representation would look like. And the zeroth order, it's first order in time, but it's zeroth order in space, right? It's constant in space. And so the expression that represents that would look like this, and would look like this. And these are just the shape functions, the products of the shape functions of the elements. And we know what those are. So if we wanted to, we could immediately define that behavior. And if we had a first order PDE, then it would look slightly different, but we could also deal with that as well. So that's the first thing to perhaps remember in our discussion of this. And what makes the finite element method quite attractive is that we can localize things by taking out a single element, which is basically a template. We can write the algebraic equations which represent the PDE, and we can use that to represent a single element, and we can then build the building blocks onto that to be able to solve it in exactly the same way as we did before. And so if we can write this expression here for a single element, then we can also write the summation of this to represent the whole system. And that's really what we're attempting to do. So that's one attribute, if you like, of finite element equations. The second attribute, which we made the point with something like COMSOL, which you'll get to see on Tuesday, is that you can use the same code to be able to solve flow problems, transport problems, solid mechanics problems, dynamics problems, elastodynamics problems. And again, one of the problems with this little software package is it doesn't actually have numbering, so I can't go to page number 47 or whatever. And we made the point that it can solve all these different solution types, and we will solve these different solution types. The one that we're working with right now is flow and transport. We have made the case that you basically have to solve, for any boundary value problem, you have to solve, or initial value problem, you have to solve for 4 things. And the 4 things are that you need to have a conservation equation. You need to have a constitutive equation. The variables that you have in your system have to be continuous within that body, if you like. And then you have to apply initial and boundary conditions to be able to solve it. And so these are the 4 things that are really written here. The conservation of mass equation for us is basically that d Vx over dx plus d Vy over dy, and if it's the 3rd dimension, dvz over dz equals either an accumulation term or 0 in the steady state. This is just another way of looking at it. Mathematically, that's what it is, but in terms of physically what it says is it says that mass in equals mass out. If stuff is going in at carrying fluid in at a particular velocity, then as it changes velocity across this small differential element, that has to be such that when you sum up all the stuff going in on the 3 faces it can go in on, and the 3 faces it comes out on the other side, because we're looking at a differential cube, they have to sum to 0. And that's the statement of that. So we satisfy conservation of mass. If density isn't changing in our system, then conservation of mass is just conservation of velocity. Continuity just says that heads are continuous. And so continuity is really just saying that dh dx is equal to this A matrix times nodal values of heads. It says that within the element that there are no sharp jumps in the surface of heads that are in the system. We satisfy a constitutive relationship, and that is that velocities are equal to hydraulic conductivity times change in head with location. Suppose if we want to be correct, it should have a minus sign in there to be able to do that. And if we satisfy all of these 3 conditions in some solution method, then if we apply initial conditions and boundary conditions to the problem, boundary conditions for a steady state problem, initial conditions for a transient problem, then we're able to solve our system. And so the reason that we can apply it not only to the system of equations that we've looked at so far, which is just these flow equations, but also to transport and to solid mechanics, is because in each of these other parallel universes, the things we have to solve are the same. The conservation equation of solid mechanics is conservation momentum, which for the steady state problem is F equals ma. Force is equal to mass times an acceleration. We could also write an acceleration as mass times a rate of change of a velocity with time, right? So this is mv is momentum, d dt, mv is the rate of change of momentum. So conservation equation for solid mechanics is basically Newton's second law. If the accelerations in our system are 0, then it's just that the sum of forces have to be equal to 0. And that's really the only problem we'll look at. We'll look at pseudo-static problems where there's no inertial effects. We're not looking at earthquake engineering in this class. And so for the cases that we'll look at, basically sum of forces is equal to 0, and that happens to be borne out by the sum of equating the amount of work internally and externally. We'll talk about that in due course. The continuity equation is that displacements are continuous, and so they have to satisfy the fact that displacement gradients du dx is equal to a ux, if you like. And so this is a gradient, and it just comes from a transformation of nodal displacements. And this is Hooke's law, nothing more. And if you look at transport, same. Conservation of mass is still required. The conservation of mass here is the amount of water or the fluid going in versus the fluid going out. Conservation of mass here is going to be the amount of mass of dissolved solvent going in and the amount coming out. Not the amount of water, but the amount of dissolved component. Continuity is that concentrations should be continuous, which would be our dependent variable. and we'd satisfy two constitutive equations. One is Fick's law. This is a diffusion coefficient. One is an advective term for what's different between transport from flow systems is you have an advective term, and then again we solve for these other two conditions. So that's basically, I don't know what the equations would be for electrodynamics, for instance, but they would fall into those similar categories, that you can take these conservation equation, continuity, a constitutive equation, put them together somehow. I guess for electrical flow it would be Ohm's law, right? Would be the constitutive law that you use. And I guess the balance law would be Kirchhoff's law, conservation of potential or charge, conservation of charge perhaps. So that's the reason why any of the codes that we work with could be used to address any of these particular physical problems. Okay, I'm just looking at my notes of what I wanted to talk about. Yeah, all right. So that's useful. Hopefully that's useful to kind of push this back in perspective. I wanted to come back. So finite element methods were developed, as I mentioned, in the very late 1950s, 57. The heyday of finite elements was developing computer solutions to be able, these are different from the Matlab files I sent you earlier, but the essence of it is being able to solve the algebraic equations that come out of this. And so there's a couple of things we can look at today before we look at ComSol on Tuesday. And those things are that there are some simple tasks that we performed when we solved the system of equations. And those tasks were actually it's probably worthwhile. You'll have to remind me of exactly where that component is, but I guess it's actually after this. When we solved our flow, so the first stuff that we solved, the solution that we worked on, it is before that, was this, right? So you'll recall this. So you recall that what we did was that we took a geometry that we were comfortable with, and that geometry for us was just two elements which had, I think, a common node that interfaced the two elements. We called these two elements by Roman numerals. We had some boundary conditions that were applied on these upstream and downstream of head. And what we did was we first of all figured out what the template was that represented a single element. And this template was something that was defined in terms of a length, a cross-sectional area, and a material property, which is hydraulic conductivity. If we knew what these things were, we knew we could calculate them from just this template, which I can barely get in here. It was 1, minus 1, minus 1, 1. And that we could apply that by basically writing our Q equals KH expression, which is this. And then figuring out, first of all, exactly where the individual matrices went. One went here, which linked up global nodes 1 and 2, and 1 and 2. And it was a straight substitution into here. And the second one came from the parts which are indexed relative to these other two components. So in other words, the template was applied on this. This was, if you like, local node 1 and local node 2 are perhaps what we should draw circles around. And the bracketed ones are the global ones. So in other words, we might have 100 nodes in a system. They'll be numbered 1 through 100. Actually, we actually measure degree of freedoms, but since we only have one degree of freedom at each of these nodes, one head or one flow rate, then we only have one degree of freedom per node. If we're dealing with solid mechanics problems in 2D, we'd have displacement degrees of freedom 2 per node, and we'd have, for a 100 node system of equations, we'd actually have 200 equations and 200 degrees of freedom. And so we deal with it that way. So make the distinction between these local nodes and this local template versus the global case. And then when we add these in, then in this particular case, I suppose these should actually be, these are circled ones because they are local, but these would actually be bracketed ones. So perhaps retroactively I should bracket these, because these are actually the global node numbers which they go into. And so we see that 1 and 2 are related to each other. And so this would be the term that is here. This is the 2. And so it goes in this particular location. And so in our particular system, these are the portions of the elements that fit in there. And so if you understand exactly what's been done here, that is really the essence of all codes. You never, of course, see it if you're using COMSOL, but if you're developing your own codes or portions to interface with it, you certainly need to know about what those referencing conditions are, indexing conditions. So we can put together a system of equations which relate fluxes and heads through this equation we can always define, and we can always put together in a global sense. Once we have the system, then all we need to know are the locations where we don't know the head conditions, or the fluxes, neither the heads or fluxes are defined. And in this case, it's only one. And so the reason for the horizontal lines on this particular chart is that there is only one active equation in this system, and it's the middle equation at which we don't know the heads. We know the fluxes because Q2 has to be 0, because the same amount of fluid is going out from one element as into the other. So by definition, the sum of those is 0. And so we're left only with this one equation. And if we solve that one equation, what do? First of all, we write the equation out, and we take the terms which relate to this term here onto the left-hand side, which I think is this. This is the equal sign. And we take this term here, multiplied by this, also onto the right-hand side. We solve for the one unknown that we have, which is the head. And then once we have that done, we can resubstitute this value back in to get the other terms. So that's the basic solution sequence. And so that's really all we need to do. We could, of course, if you wanted to think about it this way, and it's useful to think about this, we're really solving the system Q equals KH. If you want to think about it this way, what we could do, I didn't really leave myself enough room, so let me erase that. What we could do is we could multiply both sides by the inverse of K. And if we do that, then by definition, the inverse of a matrix in itself is just the identity matrix. And we end up with a magnitude of basically being able to figure out what this is, because now we know this is the identity matrix, just ones on the diagonal, multiplied by a flow matrix, which we know some of the terms of, and an inverse of this conductance matrix, which we can also get because we knew what K was in the first place. So now by calculating what this is, and we only have one term that we actually know in this particular case, and we'd only need one term, we could actually solve for the system by doing that. And so you could see that here is that, so you can see it that other way. So that's the other way that we can think of doing it. And so that is basically the system. So 1, figure out what the template matrices are. 2, figure out for each element what the magnitude of that matrix is. 3, assemble it into a global system. 4, rearrange the matrix equations cognizant of the things that you know and the things you don't know. Solve for your unknowns, which is 5. Once you know the remaining unknowns, you can resubstitute it and get the other terms for the fluxes, which is item number 6. So that's kind of the sequence of things we'll do. So I think it's up, right, that we have to go to get to the Matlab script. So many hopefully are familiar with Matlab. You can play around with these terms. You should get exactly the same things out of it that are here. This is driving me insane, apart from this, but anyway, so. All right, so let's come back to things that were related to what we just talked about in terms of setting up these geometries. And so this came from somewhere else. I can't remember where now. There's a nice little book on finite elements, and I can't remember who the authors were. Actually, I think it might be on the syllabus. I think it's Catan. Yeah, okay. So number 3, the book number 3 on your syllabus was by P.I. Catan, Matlab Guide to Finite Elements, an interactive approach. It's actually quite an interesting book. Not that I've ever really used it, but I did steal a couple of components from it, which you see here. So just some basic ideas. So Matlab, as you probably know, allows you to write functions, which are kind of like subroutines, what I would call subroutines in Fortran. And a function allows you to be able to define a function, which you give a name to, which allows you to transfer a particular variable and get it to write an output. And so this function allows you to define, when you write it, as you write it down here, as a function, put a number in here, and it will take that number, I guess it would be referred to as an argument, and it would apply the argument to the function. So if you put 1 in here, it would make a matrix which was 1, minus 1, minus 1, 1. So in other words, it would make this 1, minus 1, minus 1, 1. And I think it does it as rows through columns. So this would be the top row, and this would be the second row. I can't remember that exactly. So that's one of the things that we need to do, right? Because we need to be able to make this matrix which looks like A, K over L, 1, minus 1, minus 1, 1. So clearly, if we put a term in here, which is this scalar value of AK over L, whatever that may be, then it would return this K matrix. It would be this. So take the template, be able to develop the conductance matrix out of it. The second term, we want to be able to take the K matrix and we want to be able to write it globally for our particular case. Whoops. So for our geometry that we're working with, it has to be 3 by 3. This, I suppose, we would put onto it 1 and 2, 1 and 2 only, right? This one has more numbers. And so what we'd like to be able to do is be able to put our matrices in the right place for 1, minus 1, minus 1, 1. And also in the other place for 2, minus 2, 2. And so I think you get the picture. And so this is exactly what this does. So it takes a matrix which we defined, which would be the global matrix, this one, 3 by 3 in this particular case. It takes a 2 by 2 matrix, which hopefully we've defined here. So I guess kind of this would be this second one here. And it would define what the values of these global rows and columns would be. And so for the second element here, this would be 2, and this would be 3, I think. And what it would do is it would take this overall matrix and it would put these in the right location. And that's a characteristic mechanism that we need for finite element code. So those are the two main portions. and then we can do some multiplication. So if we want to be able to take, Q equals KH, then in the parlance of this, it would be that Q is equal to K times H. That's an asterisk. And so in the parlance of Matlab, it figures out exactly what these are as matrices. And you have to make sure that if you're doing that, I suppose, that the sizes of these things are right. So in this particular case, if we define things as Roman Catholic, as I think of things, RC, so I think this index here refers to the rows. This refers to columns. Rows, columns. I guess that's also kind of Roman Catholic. Oh, I never thought that. Then this would be 3 by 1. 3 rows and 1 column. This would be 3 by 3, just because it has to link it. And this would also be 3 by 1. So they have to be the right size. So in doing those multiplications, we have to deal with that. And so this is just something that takes in a value of a local could be a local or global stiffness matrix, and magnitudes in our cases of heads, I suppose, and it comes up with values of flow rates. So this would be Q, right? So those are actually the basic transformations that you need to be able to master. So coming back to our problem, or the solution we want to do. So these are the commands. So this would take this stiffness matrix. I guess I'll keep it up at the top. So if we take this, just to remind you of this geometry, (25), 20, 1, 2, 3. These are the global numbers. This is the local matrix, which looks like this: 1 and 2, head 2 and flux 2, head 1 and flux 1, and the material properties. What were our terms? This was K equals 1, K equals 2 times 10 to the minus 6 meters per second. Area, I think, was 10. I think the length for each one was equal to 10 meters. And so these are the individual components. I'll do the first one. You put this in as an argument, and K1 comes out as equal to 10 to the minus 6 multiplied by 1 minus 1 minus 1, 1. K2 comes out as 2 times 10 to the minus 6 times the same operator, if you like. This makes a 3 by 3 matrix, which is equal to 0. As you can probably imagine, 0, 0, 0. And this is going to be the global conductance matrix that we use. And then these two terms together, if we look at it, take the K matrix, and it's equal to something that looks like this. And we've already said that it has zeroed components in it. and it has locations here for these terms. And it's going to do exactly this. So index 1 is here globally, 2 is here globally, and 3 is here. 1, 2, 3. And it's saying that it takes the big matrix, K. It takes the small matrix, which it knows what it looks like, which is just a 2 by 2 matrix which has these terms in it. And it wants to put these terms for location 1. I did it again, right? I should have bracketed this in our terminology. These are the global ones, which are bracketed. And it takes the indexes, 1, which is this term here, 2, which is this term here, and it knows exactly where it wants to put it. It puts it in these 4 slots. And that is what we called before as element number Roman 1, which is this, versus Roman 2. And those are added in the right place. It goes to the next one. It takes the first one here, which it indexes as 2. It takes the second one here, which it indexes as 3, which is here. And so what it's going to do is, I can do this, is to put it exactly in this location here. And so it has all these terms in here. And so actually it's this, right? If I drew this again, this top term of this K matrix is this through to here. This bottom term is this through to here. And absolutely, they come from this term and from this term. Okay. We now have a conductance matrix, and we want to solve the rest of it. We can define our Q matrix. If I zoom up. So we're going to now want to solve, if I roll this, can you see it if I make it a bit smaller? Can you see that? How's that look apart from being scribbled on? Is that big enough for you? Looks marginally big enough. I see shaking heads. Was it big enough before? Marginally? All right. So yeah, it's an interplay, I guess, between what we get on the screen, and of course it'd be useful if you can see it, rather than me just talking about it. And so now what we want to do is we want to get this. So we're going to solve Q equals KH. And so now we know that Q is going to be a 3 by 3 matrix. We know that 3 by 1 matrix. We know that K is a 3 by 3 matrix. And we know that heads are going to be that. So we put our terms in here. Initially these are zeros because we don't know what they are. We certainly know that Q2 has to be 0, but we actually don't know what these are yet. We know that our heads are, these may be backwards, is that right? Oh no, that's right. No, this is downstream. So 1 is downstream, so this, we know this is 20. We know this is 25. And we don't know H2. Put it for 0 now. So now what? Spring element, oh, did we have spring element forces in there? Oh yes, we did. So spring element forces is just a matrix product of 2 matrices, okay? So what's this going to do? So Actually, I'll explain. Remember what we did last time? We know that we only need to solve for this central equation. We only have one unknown here. And so we're only interested in solving for this central equation. It happens to be that this central equation is H2, but actually we put it in as 0. So what we can do is we could multiply each row of this by this and subtract it off to the left-hand side. That's exactly what this is doing. It's taking the original value of Q, it's going to multiply the K matrix times the H matrix. This term will not be H2, it'll be initially at 0, right? And so when you multiply these and subtract it off to the left-hand side, you basically move everything to the left-hand side of the equation. We're not interested in the top equation. We're not interested in the bottom equation, but we are interested in the intermediate one. We do it for all of them, but we don't care about the top two. When we do it for the middle one, then we'll get this term here. So if I write this as, put the 10 to the minus 6 outside, and this is 1, 3, 2, actually minus, right? So it'll give us 20 times minus 1, subtracted off the left-hand side. 20 times minus 1, subtracted. It'll give us 0 times 3, subtracted. And it'll give us 25 times minus 2, subtracted. And that'll be the terms on the left-hand side. This term is 0, so it doesn't get carried. And so we've actually made, so what we've done is we've correctly made the Q vector the right way it is. Don't know why we do this. Don't know why we do that. Anyone got a thought of why we would do those two things? No, don't quite understand. And then we solve our equation by setting H2, which is the second row in the first column. It's a one-column matrix, right? So this designates the fact that it has one column, and the second row, so the second row of that one column, is equal to Q21, which is the second row and the first only column of Q, divided by the conductance matrix. So we're dividing both sides by K. So in other words, if you remember, we talked about doing this. Q equals KH. We can do this. K inverse. K inverse. This is the identity matrix. 1, 1, 1. Just 1 on the leading diagonals. In which case, this now gives us this. So this inverse, this term here, or this operation, is basically this operation here. And that gives us a value for H. And then if we take the value of H, just put it in exactly the right place here. So if you remember, anyone remember what this value H2 was? That's very good. I was going to say, I've been teaching this class too long if I know what it is. But that's exactly what it is, 70 divided by 3. So it'll now have the right term in here, so that now when you multiply H by K, you're merely multiplying it by this matrix, which has all of these correct terms in it. Let's do this just because I can. Yeah, why not? This is 1, minus 1, and this is minus 2, 2. You'll notice that these are zeros. They're not populated because they don't physically have element connections. We'll talk about that maybe later. We won't confuse this conversation with it. So now when you multiply the K matrix by H, which is this, K times H, it automatically gives you all of the components of this other term. That's it. So those are those half dozen steps which are all put together to be able to work this system. So this is actually implemented, I suppose. So let's just quickly go through this. We calculate K1, which is for element 1. We calculate K2 for element 2. We zero the K matrix. We take the first element matrix and put it into it, and it goes into, so this would be a matrix that would look like this right now. This would be the first two terms that go into it in the right place. We take the next step by taking the next component, it's not all of this 3, but it's 2/3 of that 3 that goes in there, and so that's the next part. We zero the Q matrix, we put the right terms into the H matrix, we perform the calculation Q is equal to Q minus KH. In other words, we move everything off to the left-hand side. In our middle value for H2 we have 0, so it doesn't give us the wrong results. So that gives us a new Q matrix. The K matrix should be unchanged. So this is still the same K matrix. I guess the reason for printing K is it prints out the matrix. So just to show that the matrix here for K and the previous matrix for K that we had is completely unchanged. I guess that's the proof of the pudding. To show that the H matrix is unchanged. And then to do the calculation that is Q equals KH, K inverse, and in other words, this is just the identity matrix, so this is equal to this. So we have a value for H. This is 70/3, which was our previous solution. And now if we know what all the values of H are, we can do the multiplication. And if you remember, our result was 1/3 in and 1/3 out times 10 to the, I think it was 3 times 10 to the minus 6, which is 1/3 times 10 to the minus 5, which is the same. So that's it. So that's how finite element equations work and using a Matlab script. So that is the first thing that I want to deal with. There are slightly more sophisticated ways of doing that as well. And so obviously, if you use this method, you'd have to compile all of these. If you had 10 elements, you'd have to do this K-stiffness thing 10 times and add it in 10 times. And so that's not quite the way that finite element codes work in a mechanistic way. So the next step up from this then is to codify it in a slightly different way. I want to get rid of, actually I want to get rid of this, but I guess I can't. Right. So, so the next step up, if you like, again looking at some more coding, is to take this and define it in how Matlab would solve it. And any finite element code basically does the same steps. And what it would do is it would define the problem that you're solving. And the particular problem we're solving is the one we've talked about so far in terms of conductance matrix. It would want to know what the information is that define this matrix. So I guess the first thing is global information. For mesh. Secondly would be the mesh geometry. Third would be material properties. Actually, 3 and 2 might be switched, but it doesn't matter. And 4 would be initial conditions, which we don't have yet, or boundary conditions. And so that's the typical solution method. And so usually these models work from, if you like, a core to the code. And maybe something that now looks at, goes to get input. Supplies this to the core, and then the core goes out and repeatedly interrogates, if you like, what we'll refer to as element subroutines. So in Matlab they'd be called functions, but in Fortran, maybe even in C, I'm not sure, they'd be called subroutines, which is just maybe perhaps just a longer function, bigger, more complex function. And so that is the way it is kind of localized. So the 3 files that I sent you, if you receive them, one is the core, FEM, EGEEfem, which we're looking at right now, is this core computation part. One was an input file for this one-dimensional 2-node element. And the other one was a specific element subroutine, which will get called multiple times to be able to do all the functions that we've talked about. And so, briefly, in looking at this, the problem that we're solving is Q equals KH plus S H dot. If we're solving solid mechanics problems that had inertia in them, we might be looking at a mass matrix with an acceleration term. So ignore that I'm writing this, but if you're interested in what this terminology is, solid mechanics equations have a stiffness matrix, a force vector, and an inertial component. So in other words, when you're shaking a building, the period at which it takes is controlled by the stiffness of the building and the weight of the upper stories. And the weight of the upper stories gets accelerated as the base is moved, and we're solving for that term. We won't worry about that now, but that's kind of the bigger picture. But just to look in overview at what's going on in this kind of core routine is that the first part is what are the big picture components that describe our system. How many nodes do we have? How many elements do we have? How many degrees of freedom do we have? And in the stuff that we do here, it's not so important, but most commercial scale finite element codes, actually, you can, if you know how many elements you have, how many nodes you have in your system, and if you know how many degrees of freedom you have, in other words, for our head finite elements, we have 1 degree of freedom per node. If you know those variables, then you can calculate exactly what the storage is that you need. And usually the storage is taken out of a single one-dimensional array. So a vector that's 10,000 characters long, and the parts that are needed for the coordinates of the elements take up a certain amount of space, and you can calculate how many storage spaces you need to take the coordinate data. You can calculate how many storage spaces you need for the material properties. You can calculate how many storage places you need for the indexes moving between the global elements and the local elements, etc. And so what that allows you to do is, instead of making a whole bunch of arrays that you change the size depending on how big the problem is, because you don't want to use any more core computation time than you use otherwise, is that you just dimensionally number this one big array, and it automatically divides this one-dimensional array up into the right parts for each part. And so that's how most commercial, large-scale finite element codes where it doesn't matter for us. But in this case, we'll define how many nodes we have, how many elements we have. So nodes are 3. We have 2 elements. How many degrees of freedom we have per node, which is 1. How many nodes per element, which is 2. How many materials we have. We have k of 1 times 10 to the minus 6 and 2 times 10 to the minus 6. How many dimensions? It's a one-dimensional problem, x only, 1. And how many equations do we have? We have 3 nodes. Each node has 1 degree of freedom per node. 3 times 1 gives us 3 equations. We have a 3 by 3 matrix. So we do some things. We make all of our matrix 0. This is our conductance matrix. This is our flux vector. What we're dealing with here is Q equals KH. For solid mechanics, that is equal F equals KU. And so forces are fluxes. Displacements are heads, just by convention. And this is U dot. So this is this, U dot and U double dot, just by terminology. What else? Okay, so that's kind of setting up the problem. We input some material data. So we know that element number 1 has a hydraulic conductivity of 1 times 10 to the minus 6. And so we have a material array that stores all the data. And we don't need to say anything about what that is, other than it is just an array called this. We have an array that stores coordinate data, the x, y, and z coordinates of the nodal points. And we have an addressing array which allows us to take our model, which is written as nodes 1 bracket 2 bracket 3, the global degrees of freedom, and to link it with the local degrees of freedom, 1 and 2. So in some cases, when we're looking at element number 2, this is perhaps the case, and that's what goes in here. And so, importantly, so I mean, this is just information. You may or may not ever use this, but I think this is interesting to get some appreciation of the logic which is used. There's no implicit information about whether you're getting a modulus or a permeability or a Fickian diffusivity magnitude. It's all just some numbers that go in some places in arrays. We said that when we solve these problems, we have element subroutines. So it's these element subroutines that will actually input some of the data and choose what data it's physically asking for in the data input file. Because clearly, if you're solving a problem where you're solving solid mechanics and you need modulus versus you're solving a flow problem where you're solving for, you need permeability, then you're going to need different data files to be able to accommodate those. So that is all taken care of in the particular element subroutine, which perhaps is probably worthwhile looking at. So you take the data in, let's not worry about all the other things that are done. It's just the same things that we've already done. You'll see that this code is only, it's probably 50 lines of code. It's really nothing. But this is the basic guts of really quite a capable finite element program. Actually, you'll recognize this. Remember when we talked about solving the system of equations before? We had Q is equal to Q minus basically KH, K times H. That's basically this. And so we don't need to deal with that now, but you'll recognize some of the features. All right. So we've made the point that we have these three components running out of time. We have the core, we have some input information, and we have element subroutines. if we look at the data file, bless you, the data file looks like this. For our particular problem, recall the geometry was 1, 2, 3. I'm drawing it inclined, but actually the x-axis has to be through here. So what do we know? How many nodes do we have? We have 3 nodes. How many elements do we have? We have 2 elements. How many degrees of freedom do we have at each node? We have head, which is a scalar. How many nodes per element? Well, our individual template looks like this. So nodes per element is 2. How many materials do we have? Well, we have material number 1 and we have number 2. And so that's 2. And how many dimensions? X coordinate only. No Y, no Z. That's the global stuff that sets up the system. The nodal data. We have 3 nodes. We've told it already that we have 3 nodes, which is here. So we're going to need information for 3 nodes. We have a node number, 1, 2, or 3. We have a node X coordinate. We don't have Y or Z coordinates. Node number 1 is 0. You remember the length of the element was 10. So node number 2 is 10. Node number 3 is 20. Okay. So we've got some global data. We've got some node information. We have nodes, but we don't know how they're linked with elements. So the next piece of information is the material property data. We have 2 materials, which is this one here. So we have to have 2 material property data cards. That's a hark back to when information was put into a computer on cards. So we're going to need 2 of these cards, and we can define in this element subroutine. This is a particular element subroutine for our 2-noded element. We're going to define what the properties are that we want to be able to define it. And those properties are going to have to be hydraulic conductivity, and it could be cross-sectional area, A, and it could be some other parameters. We don't need length because we've got length here. It could be length if we wanted to have length. So parameter number 1 is hydraulic conductivity. We've defined that. Parameter number 2 is cross-sectional area A. We've defined that. And it just goes here. So 1,1 is the code for the element type, this particular element. This is hydraulic conductivity of element number 1. This is cross-sectional area of element number 1. For element number 2, 2 times 10 to the minus 6 is hydraulic conductivity. Length of the cross-sectional area is the same, and we don't need the other ones. So that's the information for material properties put in. So we know the nodes, we know something about the properties, but we don't know how the nodes are connected to each other and what the geometry of this looks like. So the next is, for want of a better term, element association data. So we're going to take each element, element number 1 and then element number 2, and we're going to tell the code what local number 1 is associated with in a global sense. So that's here. And also what material it's associated with. So this is material number 1 for element number 1, material number 2. So if you like, this is material number 1 and material number 2. Of course, material number 2 could be applied to other elements if we had it in the system as well, and number 1. So this is element number 1. It has material type 1, which is, I'm going to overprint as a Roman numeral. Right? It's this term here. And so it'll associate these hydraulic conductivities with that. And it knows that node number 1 locally is global node 1. Local 1 is global 1. Local 2 is global 2. This are these 2. Element number 2 is more challenging. It's material type 2. And local node 1 is global node 2. And local node 2 is global node 3. So in other words, the positions of this would be node 1, this would be node 2, 3, 4, if there were those. And so now it knows how to put it together. And now we want to also define what the constraints are. Remember, we did different things with heads if we knew them or we didn't know them. And so the convention is that Q equals KH, F equals KU. If the displacement is fixed, if head is known, then we put in a 1. So we knew the head at node 1 was 20, so it's 1. We don't know what the head is at node number 2, and we do know the head at node number 3 is equal to 25. And we don't know this, so it's not fixed. And we know the magnitudes of those boundary conditions. We know that this is a prescribed head of 20. We know that this is a prescribed flux of 0. And this is a prescribed head of 25. So you remember that the K matrix that links these, uppercase K, was linked to don't know, 0, don't know, and 20, H2, 25. So this is representing the fact that we know these heads, we don't know this head, and so the value that ends up getting stuck in here is actually the flux, which we do know, and we index it with this. So that's basically the input. We've run out of time, but just in case you want to mess around with this, because you can, this uses FreeMat, and all these 3 programs are loaded in there. The master code, the input data file we've just looked at, and the element subroutine which we haven't looked at. But if you look at this, you'll see exactly what it is. We calculate what the conductance matrix is from the area, the conductivity, and the length. We make sure it's 1, -1, -1, 1, and then we send it back to the main program. And so if we run this, which you'll see happening below, then all it's done in this particular thing is it's taken this information in. Hopefully it's done it right. Actually, it might not have done. Oh, yes, it is. Just a matrix that looks like it could be right. Second conductance matrix, a global conductance matrix that looks like it could be right, etc., etc. And you have some fluxes coming out of this that are the right ones, I believe, and some heads within the system. Can you see that at all? Yeah, I'm surprised. I can't see it. It's sitting right next to me. And these values, this is 70/3. So maybe give that a shot. Try and get it up. I think certainly it's probably easier just to download the whole EGEEfem thing from the website and to start importing that into Matlab or whatever you feel comfortable with. This is just a free version of Matlab. It'll work seamlessly, I think, as an M file in Matlab. Be a curious thing to play with. But the point today is that to make the case that this is why finite element codes can solve flow problems, solid mechanics problems, because they define things in a very specific way, and because also the equations that represent those systems are really, really very similar to each other indeed. Governing equation, a conservation law, constitutive law, and boundary conditions are basically the things that all of them do. And so that's why it works in that way. All right. Yeah, great. That was fun. I enjoyed doing it. Hope you enjoyed doing it today.